Okay, welcome to the second session of the workshop. We are very happy to have Ilya Mirolo. So Ilya was in Stanford, but he has a lot of actual connections with industry. He was at Microsoft Research, at Google. Now he's actually at Facebook AI. He has a lot of work, and I'm personally a huge fan of his work on differential privacy. And today he's going to talk to us about crypto and ML, just getting started. So Ilya, please go ahead.
Do you see the title slide?
Yes.
Okay. Thank you so much for being here. Excited to see you all. And today this is the agenda of my talk. We'll talk about MPC and where it falls short. Differential privacy, of course, like if you're playing bingo with whatever words people are going to say, kind of please check out bingo, differential privacy. Two interesting projects that I want you to learn about, and we'll conclude with some observations about how crypto mindset is relevant to ML research. A very rough trajectory for the talk is that we'll start in theory and we'll go deeper into more applied material. Or depending on your perspective, we'll start deep in theory and we'll soar to practice. So MPC and ML, like this is what we are here for.
Ilya, sorry, I think we don't see the slides advancing.
You don't see the slides advancing. So you missed my joke. Let's do it again.
Yeah, I could see them earlier.
Yeah. So I'll do the same. Okay, and just one sec. And now can you see it? Can you see the title slide?
Mm-hmm. Oh, perfect.
Okay, so now do you see the agenda?
Yeah.
This is the rough trajectory of the talk, starting high in theory and going deeper into applications. Or depending on our perspective, we can start in theory and soar to practice. Okay, so MPC and ML, this is what we are here for. And the question that is on many cryptographers' mind when I tell them what I do is the following. Haven't we solved privacy already? Indeed, it's been almost 40 years since the introduction of the GWAS millionaire problem, followed by GWAS garbled circuits, celebrated protocols of GMW, BGW, more recently fully homomorphic encryption, speediest protocol to name just a few of the highlights of this line of work. However, the answer to the question, which might as well be the title of the entire talk, that despite all the progress so far, it is no. Let me explain. The standard MPC guarantee is crisp, powerful, and provides for a very neat API between different research communities. Yet, I want to argue that this guarantee is both too weak and too strong. It is too weak because it washes its hands of the leakage from the output of the functionality. As security professionals, we should own the problem rather than offload it to others who might be less equipped to deal with it. it is too strong because no information is leaked may be an overkill once we are resigned to the fact that some information is going to leak from the functionality's output. So it probably wouldn't come as a surprise that if I say that differential privacy plugs at least some of the holes in the MPC guarantee. Whereas MPC takes the functionality as a given, differential privacy is concerned with what functionalities are safe to compute. It first appeared in the TCC 2006 paper, and the notion of differential privacy is rightfully considered one of the more consequential crypto papers of the decade. And here's a picture from the TCC Test of Time Award ceremony from 4 years ago. If you're interested to learn more about differential privacy, I encourage you to check out Cynthia Work's beautiful invited talk at Eurocrypto last year. Informally, the definition of differential privacy captures the following property of a randomized algorithm. For two databases that differ in a single person's contribution, D and D prime, the output of the mechanism on D is nearly the same as its output on D prime. More precisely, the definition requires that for all possible outputs, the two distributions must be multiplicatively close to one another. In this talk, we'll be using the epsilon delta DP guarantee, which has two parameters, epsilon and delta. Think of epsilon as a small constant that bounds information leakage, and delta as the probability that the guarantee fails. It's not precisely kind of the precise semantic of the definition, but this is something convenient to keep to have in mind. And typically, we want our epsilons to be of the order of 1 or smaller, and deltas to be much smaller than the inverse of the size of the data set. I want to summarize this with this dichotomy between MPC and differential privacy by saying that MPC answers the how question, while differential privacy provides answer to the what question. It suggests a natural paradigm for combining differential privacy with MPC. We start with the actual functionality that we'd like to compute. Then we find a differentially private approximation to the target functionality. Finally, we execute it in an MPC environment with appropriate guarantees. After all is said and done, can we claim that the end result is differentially private? And you're probably guessing that the answer is not really, or at least not if the MPC confidentiality guarantee is computational. The reason for that is pretty obvious. If we examine the definition of differential privacy, it is an information theoretic notion. Hence, MPC plus DP, the combination, is strictly speaking not differentially private. It calls for a relaxation of the definition that is naturally called computational differential privacy. If you just follow your nose, then it is quite natural to replace the worst case test with the computationally efficient one. However, an equally valid and intellectually honest approach is to ask for a simulation-based definition where we require existence of a simulator that is truly information theoretically epsilon delta differentially private, but not necessarily efficient. And that simulator is computationally distinguishable from the real-world mechanism. As is relatively common, the simulation-based definition trivially implies indistinguishability-based one. However, and this is still an outstanding question, we don't know where the converse holds. I conjecture that it isn't, but I wouldn't be surprised if the opposite is true. And watch out for this like large question mark at the on the slide. I'm going to mark open problems with kind of with this symbol. Having introduced not one, but two definitions of computational differential privacy, we'd like to understand whether it allows us to do anything that the standard definition doesn't. For the two-party case, consider a canonical task in statistical analysis of computing the L1 distance between two Boolean vectors. If both parties want to preserve differential privacy for their inputs, then under the standard information theoretic notion, the error scales in proportion to the square root of n. Here we kind of make this, introduce the subtle assumption that our epsilons are constants, so we are going to ignore them for the time being. However, even under the stronger simulation-based definition, the error behaves like 1 over epsilon, which is independent of the size of the input. The hard part is the low bound on the error of the information theoretic protocol. For the computational protocol, the two parties may just simulate a trusted third party that performs the computation. Or if we feel like it, we can use a more efficient, or we can design a more efficient protocol along the lines of the private cardinality of set intersection with differential privacy. To sum it up, I want to paraphrase Al Capone, who put it best. You can get much further with the kind word in the gun than with the kind word alone, where the kind word is differential privacy and a gun is cryptography. Let's consider the paradigm of designing MPC that implements a differential private algorithm. A typical pattern is that of the target functionality being simple and easy to compute, even in the MPC setting. The bulk of the work goes into implementing the differential private mechanism that often involves adding some amount of noise from a particular distribution. Now I want to make the following observation. And that's kind of important, bear with me. The noise distribution is not required to be, say, Laplace, as long as it satisfies certain properties. Its probability density function need not be continuous. Here is an example of a real example of the so-called stairway mechanism. It need not be symmetric. It can be a distribution that doesn't even have a name. It can even be this. Not really, but you get the idea. More importantly, the distribution need not be even well defined ahead of time. Its particular instantiation may depend on the adversary's actions. So instead of designing MPC and differential private mechanisms in isolation, I want to call on this community to investigate approaches that meld together MPC and differential privacy in a way that optimizes resources and accuracy. I want to stress that it goes further than identifying differentially private mechanisms that are easier to execute in the MPC environment, although this is an important direction in its own right. Instead, can we imagine mechanisms that are not just mechanical combination of MPC and differential privacy? I'll give one such example when we'll be speaking about anonymous channels. Do we have more? Yeah. Instead of designing, let me don the complexity hat for a few moments. There's a vast literature on understanding the fine structure of secure multi-party functionalities. On this slide, I summarize progress in classifying complete, finite, two-party functionalities in the information theoretic setting. if we think of differential privacy as a protocol constraint, meaning that allows some bounded amount of leakage from the transcript of the computation, our present understanding is very limited. For instance, we can't even tell whether computing an AND of two Boolean inputs better than what is allowed unconditionally, whether this functionality gives us oblivious transfer. Recall the protocol for computing the L1 distance between two Boolean vectors. We have a strong low bound on the error of a DP protocol, where differential privacy is the standard information theoretic notion. Computationally differentially private protocol that beat that bound are based on powerful public key primitives. Is this really required? In other words, does a better than information theoretic protocol for computing distance apply existence of oblivious transfer? Before I talk about imminently practical ways of combining cryptographic tools and differential privacy, I need to introduce two principal models of implementing differential privacy. The standard or central differential privacy is the familiar curator-analyst model, or like the server-client model. The curator has unfettered access to the database and protects its privacy by mediating the analyst queries. We contrast it with the local differential privacy, where privacy is imposed by individual participants who each keeps a watchful eye on their own data. Being cryptographers, of course, we like the more distributed setup much better, because it puts a lot of, like the alternative, the central differential privacy, puts a lot of trust in the analyst. And it creates, for instance, it creates this one central data set that combines everyone's data and can become a target can become a high value target for attackers, hackers, or inside attacks. One way of splitting the difference between these two models is to invoke MPC. Let the participants in the protocol simulate the trusted third party that implements differential privacy. It is practical for a small number of parties, but doesn't really scale to millions or billions of people. Can we do something cheaper? This like MPC, splits the difference between these two models. And the question is whether we can do something cheaper, but more scalable. I'm going to talk about the approach known as the encode, shuffle, analyze architecture, or equivalently, the shuffle model of computation. It assumes existence of an anonymous communication channel. Its main insight is that an anonymous communication channel transforms a relatively weak local differential privacy guarantee into a quantitatively much stronger central differential privacy guarantee. This phenomenon is called amplification by shuffling, and roughly it takes a local epsilon differential privacy guarantee into an epsilon over square root of n central DP. Without the anonymization channel assumption, the strongest statement one can make about central differential privacy is still pure like epsilon differential privacy, right? So just like let me walk you through this statement one more time. If we start with with epsilon differential privacy that is imposed locally, and all participants send their data to the central data set, the strongest statement we can make about the central data set is that it still satisfies epsilon differential privacy. In contrast, if before doing that, the parties put all their data in a single box shake it vigorously, and pass it on to the central party, all of a sudden, the central differential privacy of this box becomes epsilon over square root of n. I'll illustrate the power of this approach with a picture, or actually 2 pictures. On the left is a mobility map of the New York City. It is obtained by applying amplification by shuffling, which takes an epsilon of 13 local differential privacy and lifts it to the central differential privacy of 1. In differential privacy, the smaller the better. Epsilon of 13 is very, very weak. Epsilon of 1 is something very meaningful. On the right, the same data is reported with local differential privacy of 2.0. And there's nothing but noise. As a side note, some of the ideas used in more recent papers on privacy in the shuffling model go back to a much earlier work by Eshai, Kushelevich, Ostrovsky, and Sahai, some of whom are present even on this meeting, who demonstrated constructions of many cryptographic primitives using the sole assumption of the existence of anonymous channels. Some of the results are feasibility proofs, such as constructing a generic NPC secure against the active minority, but for some, just as we do here, they improve efficiency of the resulting construction. One example that they give is a multi-user private information retrieval protocol. Although I should add an asterisk that the multi-user peer requires two-way anonymous channel compared to our setup where we assume just unidirectional anonymous channel. There are multiple options for implementing anonymous channels: cryptographic solutions such as mixnets, secure hardware, dedicated services, or organizations. The beauty of anonymous channels is that they are trivially composable and can be mixed and matched arbitrarily. Of course, it raises a larger question of identifying other natural and easy to implement primitives that split the difference between local and central differential privacy. I think of it as a systems and theory problem of defining the right interface and making the full use of it. In the MPC literature, like the very rough analogy would be beaver triples for BGW protocol, where we put the hard work into getting these triples, for which the rest of the protocol flows relatively easily. Now I'd like to switch gears and talk about two exciting projects that approach privacy-preserving ML from the ML perspective. Cryptan, developed by my colleagues in Facebook Research, is a fully open source platform for research at the intersection of ML and MPC. It targets ML researchers who are not cryptography experts, interested in experimenting with ML models using MPC techniques, and getting a realistic view of what is possible, what is difficult, how efficient these techniques are, etc. It is based on secret sharing, BGW and beaver triples, which is compatible with the speediest, which is very much compatible or inspired by the speediest paradigm. It extends PyTorch, which is a leading ML framework, and it implements what is really table stakes for ML systems: reverse mode, autograd, GPU support, etc. Cryptan's ambition, which is very close to being fulfilled, is to make switching from PyTorch to the Cryptan backend as easy as replacing the import statement in the Python program. Here we can see an example of secure inference, which should look familiar to anyone who is experienced with PyTorch. I won't walk you through the example, but basically we load a data set, we encrypt it, and we run inference on the encrypted model. The other project which I want to highlight is more than a library. I'm referring to Open Mind, which is a community that brings together students, software developers, research scientists, and enthusiasts around creating an ecosystem whose main products are tutorials, demos, spin-offs, and importantly, software artifacts. I copied some biting words from its call for action. I'll read it out loud, so like the realistic. The world already had privacy researchers, some even in machine learning. What has been most urgently needed is community, education, and tooling to make researching and deploying privacy-preserving AI faster and easier to do. To see what makes this community tick, I reproduced news items on its main page from the last three weeks. They are community building events. There are explainers of in-depth blog posts. You may notice right in the middle that they have one about the Shafi model that we covered earlier. There are announcements of important news about software development. This one in the bottom right corner is, for instance, about integration of Tryptan that I talked about a moment ago as a backend for the Open Mind most advanced project, PySift. Getting closer to the end of my presentation, I'd like to say a few words about the biggest asset of our community, cryptographic thinking. We've long understood the importance of solid definitions to progress of the research area. For instance, the concept of differential privacy has gotten so much traction because it checks off all the right boxes that a good crypto definition has to meet. It is robust, composable, quantifiable. Another principle that we've been shouting from rooftops is don't roll your own crypto. We'd like to put privacy critical code in a small number of carefully vetted, professionally maintained libraries with foolproof APIs. I didn't have time today to talk about these projects, but I want to particularly highlight the fledgling OpenDP library, whose very name, OpenDP, self-consciously riffs off OpenSSL. Development of this library is coordinated by Harvard, supported with a very generous Sloan Foundation grant, with Salil Badan as its co-PI and a small cadre of professional staff. Of course, the crypto conference would not be nearly as exciting without its cryptanalysis section. It has been one of the foundation principles in our community that in order to make progress on defenses, we have to understand attacks better. It's not a coincidence that development of differential privacy was preceded and shaped, really guided by several landmark attacks on privacy. In no small part, the definition of differential privacy emerged as a way of escaping the conditions of these attacks. Closer to the topic of PPML, of privacy-preserving machine learning, there are interesting works on various attacks that consider different privacy aspects of ML systems. I just mentioned here attribute and membership inference, as well as modern version attacks. In this spirit, I'd like to invite you to the presentation of a paper that brings ideas from differential cryptanalysis to model extraction for deep neural networks. The talk by Nicholas Carlini is already available for watching. It got really cool visuals and identifies important open problems. I want to conclude by summarizing my main points. Differential privacy and MPC answer complementary question of what and how. One relaxation of DP, computational differential privacy, is a particularly good fit for combining it with MPC, especially for two-party computations. For large-scale multi-party computations, the Shafi model shows a lot of promise and good implementation potential. The crypto and open mind projects are clear evidence of demand for strong strong cryptographic solutions to the ML problem. They are getting great traction, primarily because they are meeting ML researchers where they are, where the ML researchers are, by exposing their interfaces in PyTorch and TensorFlow. Cryptographic thinking, not just cryptographic machinery, is what we can bring to bear on the hard problems in machine learning. And finally, I did not have a chance to talk today about federated learning that draws on powerful idea in machine learning, differential privacy, and NPC, all rolls into one. There are great tutorials about it, for instance, on the OpenMind website. And frankly, the topic of federated learning deserves a whole separate talk targeted at this community, because like at the heart of federated learning is some of the very interesting open topics in MPC. And with this, I conclude the unidirectional part of my presentation, and let's switch to Q&A. Thank you so much.
Thanks a lot, Ilya. That was very nice. So if you if you have questions, you can either paste them on the Zurib chat or on the chat here. The difference is that on the Zurib chat, the questions will stay there even after we close the session. Here, they will not stay.
You can also raise your hand on the participants list, and then we'll give you to ask the question.
Yes. So as we are waiting, so Ilya, I would like to ask you about Crypt10 and in general about the systems that you are building. So what models you are targeting first? Is it like a distributed model where you have more like the different parties with the different data and they want to compute a common model, or you outsource the computation to servers and they perform the calculations? So can you talk more about what models you are considering?
Yeah. So these are all important questions, and everything is on the table so the projects which I talked about are open source. They are geared towards the research community. In industry, the projects which I'm familiar with, often assume that powerful, sophisticated parties can execute, can be a full-fledged, full participants to the protocol. There's definitely an outsourced model of computation where parties are willing to outsource some of the heavy duty, the more complex part to some engine that runs in the cloud. That's also definitely on the table. And finally, there's a lot of conversation going on about using trusted execution environment in hardware, T's, for example, Intel's HDXs, as one way of parties to move their computation from their devices to a environment that is then executed in the server. So it's kind of outsourcing computation, but the computation still stays confined to a small box that is hardware protected. So the question, the answer to the question is all of the above.
I see. Okay, we're still waiting for some questions. In the meantime, can you tell us how is the experience working with the ML community? Like the people in the industry. So is it like easy? Like what are the challenges?
Okay, so sorry, I noticed that there's a question on the on the chat that we missed by Ian. Can I address it first?
Oh yeah, sorry, I don't see that question, but yeah, if you see it, please go ahead.
Yeah. So it's in the chat, or it was sent privately to me.
Okay.
Yes, feel free to send questions to the comment chat. Like, okay, so now there are like 2 questions on the chat. Ian asks that if he says, I'll just read it out loud, or you know what, I'll copy it to the chat and read it out loud for the recording. Earlier you mentioned that secure MPC is weak in that it washes its hand on X. What is X again? I missed that. And you mentioned that SMPC is the how and DP is the what. Does federated learning or homomorphic encryption fit into these questions, and so how? MPC washes its hands of the leakage from the output of the computation. It says so explicitly. It's not interested with what functionalities are being computed. In fact, if the functionality leaks the party's data completely, in the MPC world, it's called trivial. Nothing to do here. Like, we're kind of, hooray, we are done. The parties can just like publish their data and we go home. That's craziness. It's saying to people that like, we don't care if you want to publish your data or do so in a way that you don't quite understand. In fact, my co-author recently gave a talk at a workshop on theory and practice of MPC. The workshops, the talk's title was "Don't put neural networks in your ideal functionalities," and that's a kind of very strong message to the ML community, to the MPC community. Don't assume that people who are going to use your frameworks are like they know what, like they understand, they thought through the implications of putting complex machinery inside MPC. Then Abhilash asks the question of, he wants me to, sorry, I'm not sure if the, like, about the gender of this person, of Abhilash. The question is about the shuffling model, any tools available. And the shuffling is anonymous channel, and indeed that's kind of how we implement anonymous channels in practice is a big open question. The Tor community tried to solve this problem for more than 20 years, still kind of struggling, but compared to Tor, we are solving a much simpler problem, which is of a unidirectional high latency channel. For most ML applications, if it takes an hour or a day for your data to get from your like small devices to the central server, it's fine, we can live with it. For Tor, for interactive browsing experience, it's a deal breaker. So we can bring to bear mixed nets. We can use I mentioned the hardware boxes, or we can use shuffling as a service because it's such a simple API that that companies can provide. It's like sort of like virtual like VPNs is a perfect example of something that that emerged as a solution to the problem of making browsing anonymous. And then there's a question from Yu Zhang about, and again, I'll copy the question to the chat about views understanding of peer-to-peer federated learning in privacy, accuracy, efficiency, and efficiency. So federated learning, as I said, it's something that is a very powerful and like rapidly developing paradigm in machine learning. There are dedicated workshops just about that. where data is held by parties, and the parties want to train the model in a cooperative fashion. They do so by exchanging gradients, basically updates to the model, rather than raw data. And these gradients get aggregated in the process. When federated learning was first introduced by Google researchers, it assumed one party, Google, that orchestrates this this computation. Since then, OpenMind's PySift kind of makes this federated learning a much more egalitarian process, where there is no a single party that like does everything. So in some way it is peer-to-peer. But the trouble here is that if you're talking about small devices, the kind of come and join and leave. Really for a foreseeable future, we'll see implementations of federated learning that are like assume this one party that is runs the computation to some extent. Not necessarily trusted, but at least it's present, and it mediates a lot of communications between peers. Okay. Did I address everyone's questions?
Yes, I cannot see the ones that they sent you on your personal.
Yeah. So Rafi says, thanks me, which is probably a cue for turning the Zoom over to the next speaker.
Yeah, so yeah, thanks a lot. It was nice. And I think it's good to see that you're collaborating with ML experts to push this through. It's very nice. So, and everybody who has more questions, please, you can email Ilya offline. That was great. Thank you. So now we will move to the next talk. Actually, Shafi is trying to connect. I think she is not online yet.
She's still not online, yes.
Yeah, but she's trying to connect. Okay, let's wait for a minute.
If you have more questions to Ilya, that's an opportunity.
Yeah, so I didn't answer Antigoni's question about how is it working with ML experts, and that's interesting. They have kind of a somewhat different mindset. So I kind of get a lot out of demonstrating to them that, so for example, a common conversation that I have, which is, well, kind of our models generalize. So there is no privacy concerns, like they can't possibly memorize data. And like that takes some back and forth of convincing them that generalization and memorization are two different properties. So working on attacks goes a long way towards establishing credibility in ML. Like they want, they're like better respond to demonstration, like to concrete threats, than to some theoretical arguments. So I think that's one of the lessons which I've taken away.
I see. And I wanted to ask about this. So the seminars you have in OpenMind, they are public?
Everything that I talked about is open source. Yes, and open.
We can attend. So it seemed that they were like talks, right? So public can attend.
Yeah.
Oh, that's nice.
And again, feel free to kick me off when Shafi joins. I'll be. It's just like we are trying to replicate the experience of having a real-world workshop with some chat in the breaks. So Elaine asks about applications that Facebook has for better privacy for cryptan. And as kind of you can imagine, I'm not at liberty to talk about unannounced projects that have not been formally announced. So let me leave it at that. Cryptan is being developed, and yep. So rather, like, I want to point to what Google announced about its use of private center intersection, or rather cardinality of private center intersection protocol that it runs with a big credit card network of tracking conversions between tracking conversion of online advertising to physical purchases. And it's a very high-profile project that has been talked about a lot. So I think that's a very interesting use of MPC for ML purposes.
Thank you, Ilya. Shafi is now here. It's a great pleasure to introduce Shafi Goldwasser. Shafi is one of the pioneers of our crypto community. She won the ACM Turing Award in 2012. She also won the Gether Award twice, in '93 and 2001. Her contribution is very influential, and on a personal level, I always find her very inspiring. She's also a great educator. Besides the fact that she is one of the pioneers of our field, her students became also leaders of our crypto community and theoretical computer science in general. So with no further introduction, Shafi.
Thank you, Glenn. I'm going to share my screen, yeah? Tell me whether that you can see it. Can you?
Yeah.
Okay, hi everyone. I think it's supposed to be a birthday now for crypto. I got some sort of email saying that it's 40 years, which I can't exactly figure out. Well, it's I guess it's true. And I was actually in the first crypto in Crypto 81, but certainly wasn't as a keynote speaker there, but was a graduate student, first year or second year graduate student. So the talk today is about what I call, which is exactly, the kind of topic of this session, trustworthy machine learning. And essentially, I'm going to talk about sort of 3 recent papers that I'm a co-author of. So it's sort of 3 different stories about privacy, robustness, and verifiability. So this is a slide I almost always put up and say that we know that there's a lot of sort of crypto research which was done really sort of answering basic questions, and it's had a lot of impact in electronic commerce, cryptocurrency these days, cloud computing, quantum computing, at least in order to examine which problems are resilient or not resilient to quantum computers. And you all know about the factoring being quantum insecure. And my talk today is essentially going to be to try to see how crypto can shed light on machine learning. I'm going to tell sort of 3 cases where I think that that's very obvious that we can actually learn something from cryptography. The first is going to be about privacy during training. And the emphasis here is going to be in sort of making a step from, we have a lot of papers, beautiful case studies, which are really prototypes, but we need to make a move to large scale data, especially during training. The second story is going to be on robustness, how to get accurate predictions when the test distributions or classification distributions are adversarially deviate from the training distribution. I think this is usually called as adversarial machine learning. And wherever there's an adversary, sort of, I think a cryptographic perspective is useful. And I'll show you that in this work. And lastly, suppose we have a machine learning model. How do we verify that it actually is as accurate as being claimed? And can you verify it in a way that's more efficient than simply learning it anew? So this is very very similar to the type of questions we asked in verifiable computation and in delegation, but it has a twist where we're not really delegating a computationally difficult task, but there's another resource here, which is samples in the distribution, and that's the resource we want to count when we compare between the learner and someone who's verifying the model. And the work is from 3 different papers, and I will mention the paper every time I get to the particular story. So I'm going to start with the privacy story. And this is a work in a paper with Marcelo Blatt, Alexander Gusev, Yuri Polyakov, and myself that appeared in PNAS recently in May. And it's about something here, I'm not sure. Oh, okay. So privacy, right? So when we talk about privacy, we talk about the fact that we all recognize that the power of machine learning as it came in the last, less than a decade, really comes from the fact that we have lots of data, and this data is being collected by third-party servers, usually. However, it's data of individuals. And it's fairly clear that the power these days is in the hands of these third parties who collect data about us and can use the data in order to make predictions, in order to sell us ads, in order to provide good services as well. But if we want to make sure that we still retain some of the power, we have to ensure the privacy of this data. And this is nothing new, certainly not new in this session. When we talk about machine learning and privacy, there are sort of 2 places where we sort of pay attention to, or 2 phases in the algorithm. And one of them is during the training phase, when we train or when we learn, and we use the data in order to come up with a machine learning model. And then once we have the model, we want to run it on some sort of a test case. So there are lots of works. They started sort of with feasibility, then there's asymptotic efficiency, concrete efficiency, and then proof of concept. Sorry, I just keep on pressing the wrong button. But I think that really it's very clear that the challenge now is to do the training phase, because classification is much easier. Once we already have a model to test and maintain the privacy of the test case is an easier problem. And scale is an issue. So where we have to learn from lots and lots of data at a scale where actually makes a difference for applications. So in particular, in this paper, we focus on healthcare. So we don't focus on ads or financial or fintech, but on healthcare and on data-driven analytics in the space of healthcare and drug development. And here it's a specific field where really large data sets are important and data fusing is important. So in other words, different type of data should be fused together, where you might have genomic data and then you might have data about blood work of the same patients or medical records, and you'd like to fuse all these data sources together, even though they're not held by the same collector. And it also is, besides research, there's a lot of commercial benefit in this space that people are looking at. That's true for the pharma companies, for insurers, from payers. And that was also why this work is really work that was done in the context of Duality, the startup that I'm the co-founder of. And Marcello and Gusev and Yuri are all part-time, at least involved in the company. Marcello and Yuri are full-time, and Alexander Gusev is a doctor in Boston who was a consultant on this work. So in particular, within healthcare, we're looking at genome-wide association studies. And in fact, this again is not our observation. This is an interesting place to look. There's the iDash competition that's been running for a few years already, I think since 2014. And every year there's sort of a new task that is being requested to be done on genomic data which is secure. And this is all realizing that the growth of genome data overwhelmed the capacity of servers. So a lot of people want to sort of outsource this to a cloud, and that's where privacy comes in, even more so beyond collaboration. Even if it's your own data, if you don't have the power to do it yourself, you need to outsource this, and therefore you need to keep it private. And every time you'd like to run a more difficult test, maybe from chi-square to logistic regression and so forth, But usually when you look at these competitions, again, they run on small amounts of data so that the competition is well defined and people can actually attack it. So does that make sense actually in the context of genome? Of course it makes sense because we always want proof of concept, but is it enough? So if you think about GWAS, just a little details about what is it about. So, so we have a large number of individuals, and these individuals each have a genome, and they made a variation, which is formed when you're copying sort of from the parent genome, and then these individuals may have also diseases or particular traits, and you'd like to correlate these their particular genetic variants with their susceptibility to diseases or their susceptibility to certain traits. Even though we all know what GWAS is, it's kind of mind-boggling to realize that it was successfully introduced as an alternative to, like a driven hypothesis rather than finding a hypothesis, essentially in 2002. And now it's 2020. It always amazes me when I look at these things and I realize, wow, we think this has been going on for many, many years. And maybe it has many, many years, because 8 years seems to be like a lot in the context of the kind of work we're doing. In fact, even 5 months seem like a lot in the context of the life that we're living right now. But in any case, more to the point, the genetic variations are presented as something called a SNP, which is a single nucleotide polymorphism. And each one of us has roughly 5 million of these SNPs. And the way that GWAS works, it evaluates one SNP at a time, one of these 5 million, for association to a disease or trait, to a phenotype. And often you have you're comparing the case of a disease with a control where there is no disease, or just a random sample from the population. And you'd like to do a goodness of fit test for logistic regression to find associations. And you often look at odds ratio. So the chance that you have a disease given that you have a particular genetic variation, and similar if you don't. And if the odds, if you have it or you don't, are 1, then we say there is no association. And then you talk about being far away from 1, as whether it's a negative or positive association. And of course, you do usual statistics with evaluating your p-values and so forth. So GWAS is something that, as I said, really since 2002 has become sort of an alternative to having hypotheses and testing, is that you find a hypothesis by the data. These days, people talk about polygenic scores for common diseases. So that's sort of going from association to prediction. So you kind of use GWAS, and then given a particular person that has a whole bunch of genetic variations, you'd like to know by doing some weighted, clever weights being put next to these genetic variations to figure out what would be the risk of an individual having a particular disease. So this is sort of a step forward. I think this was done successfully in 2019. So that's like a year ago for coronary artery disease, where they found really that this prediction for coronary artery disease based on these polygenic scores was a very, very good predictor. And the reason I'm sort of elaborating on this is because we're living in these particular times with COVID-19, and a lot of people are talking now about organization like 23andMe and other organizations that have genomic data that launching GWASs to identify these genetic variants associated with susceptibility in response to COVID-19. So in other words, not just studying, but in general, trying to predict whether a particular individual will get the disease, and if he will he respond to it in a severe manner, mild, maybe no symptoms. So the idea here is that you'd like to associate, you'd have like a set of people who responded badly or mildly, to people who have not even contracted the disease, and you'd like to see what is given a test case, a genome with particular polygenic scores, how are they going to be susceptible to a severe form, and therefore you might treat them medically appropriately. So you're trying to understand who is at risk, and this might give you also, of course, also clues to new drugs and vaccines, but the interesting shift here is from association to prediction. All right, so how is this done? So we have on one hand individuals with disease, individuals without disease. We have their SNPs, right? And we can say for the same SNPs, so in other words, for the same variation. So let's say me and Gilad may have a particular same genetic variation, same SNP1. One of us may be ill, one of us may not be ill. So these are sort of the kind of information we have. But as we all know, since we're in the session, it turns out that you can, and this is already an old paper by Ehrlich and et al., that if you, even sharing these types of sequencing data, these SNPs, without identifiers, if you have some more information, some other types of data, metadata, such as age or the state they live in, you can sort of triangulate this and find out even the names of exactly who is being sequenced. Problem, right? Especially problem if these are collected by different agencies and we can't really trust that, you know, Dr. Jekyll is as nice and as careful as Dr. Hyde, and he may release other information like the metadata that will make this problematic. So we have this privacy issue, and then we should say, wow, that's great. You know, that's our playground. That's what crypto is about. We know how to compromise between privacy and functionality. In fact, we don't even compromise. We can get functionality and exact privacy. And we have all these cryptographic techniques. Again, this is like bringing coals to the coal sack, you know, like, what do you say? Snow to the Eskimos. Garbled circuits, arithmetic MPC, homomorphic encryption are sort of the three things that would come to mind. And we all know that there's differences between them. And the reason I'm mentioning the differences is because they will play out in why I think that this paper is interesting, the one that I'm presenting. So the garbled circuits, the assumptions are great. It's just one-way functions. The communication is not good. So the amount of communication between two parties, one evaluates on a garbled circuit of the other, is the size of the circuit. So if the circuit is large, that's not great. And this is natively Boolean. Arithmetic MPC, especially if you're thinking about, let's say, 3 servers or something, the assumptions are the same. The communication now is the depth of the circuit, and it's native arithmetic computation. So that's already doing better. Although the communication, in a minute, when you talk about applying this to GWAS, communication actually will grow with the number of users whose genome you are processing. And then in terms of homomorphic encryption, I'm thinking here this, you know, you encrypt and you evaluate and you decrypt. The assumption is worse. So the assumption is not just general one-way function, the computational assumption. So we look at LWE or ring LWE, but there was no assumption on collaboration or non-collaboration. And the big feature is the communication is small. And computation, unfortunately, is bad if the kind of computation you're doing is not a low-degree polynomial. So for some computations, we don't suffer. For some, we do. Again, it's arithmetic computation is the naive circuit. Okay, what does this mean in terms of the context of GWAS? So in terms of the context of GWAS, there's sort of these two pictures here. Can you see my cursor? I think so. There's on the left and on the right, at least my left and my right. So this is a picture actually from a paper that was written by Bonnie Berger's group, Cho et al., where they have actually applied a multi-party, secure multi-party computation in the context of GWAS. And the way they think of it is this: there are the study participants. So these are the people up here. These are the people who have genotypes and phenotypes. So think of them as individual or centers like the Broad and so forth. And then what they do is they take this data is taken and is secretly shared among two computing parties, which they call CP for computing parties, 1 and 2. And in addition, they add a third party, a computation party 0. So it's actually 3 parties. Now, there was a previous paper by Bonnet et al., where instead of 3 servers, there were 2, and they use garbled circuit. Here, they use actually 3 servers, and they use sort of the Beaver triplets. So for doing multiplications in an arithmetic circuit. And this particular server here actually is a pre-computation because of the way these Beaver triplets work. In any case, the point more zooming out, for those people who don't know what the Beaver triplets are, is that using these secret sharing, now these computation servers, 1, 2, and 3, they communicate. And as they're communicating, they're doing the secure GWAS. Sorry, where are you? I'm lost. Oh, here you are. Sorry, I pressed something. And then you do the reconstruction of the secret sharing output and you publish the results. if you were thinking about homomorphic encryption in the context of GWAS, the study participants, these people here, these stick figures, which are the same as these, what they do is they don't secret share their data, they encrypt it using homomorphic encryption. They put this all up in the cloud or some data bank, and now the cloud has a public key or evaluation key that allows them to do all the GWAS computation without any communication. And then he gets the encrypted result. Of course, this encrypted result has to be decrypted somehow. And that's a very good question. Who decrypts it? Who has the key? And here you can either share the decryption key among the 3 servers, and their computation is just to decrypt the result, versus here to do the whole GWAS computation. So it's very clear what the differences are here. The communication is just much smaller here, where here it's the size of the computation itself. And the trust assumption is whatever encryption assumption, the security of the encryption scheme, where here it's the split between the servers. So you're assuming that they don't collaborate with each other. Okay, so what can you do? Well, of course you can do all of them. So you can do either one as you like it, depending on what assumption you prefer. That is, do you trust that the servers do not collaborate, or do you trust, the assumption under the FHE? The problem is really scalability. So these schemes are very different depending on how much data we're talking about. And size of data, as I indicated before, is extremely important for GWAS. So here is, for schizophrenia was the first time where they saw that by going up from to 35,000 cases, they could start identifying some locations in the genome which were associated with schizophrenia. This is one study. And on the right here, we're saying that that's actually true for a lot of diseases. So if you think about the y-axis as some sort of a notion of accuracy of the GWAS, some score of accuracy, and the x-axis is the number of users divided by 1,000, then as the number of users goes up, and that is the number of participants, the accuracy goes remarkably up. So if you really want to use this for prediction, if you really want to use this in a meaningful way, you need to be able to scale. So before the paper that I'm talking about, there were these 2 papers which I alluded to. One was in Science, one is Natural Biotechnology. They both were based on secure multi-party computation. The first one was garbled circuits. The second one was arithmetic computations. And a joint data set here that they used in this paper is age-related macular degeneration, so an eye disease. And they have run it on 21,000 individuals with 220,000 SNPs. So the good news is that they get very high accuracy, even though they're using the secure multi-party computation. Obviously, they modify GWAS to work to be friendly to their crypto. They use something called the Cochrane-Hermitage trend test, which is, again, is a test of fitness. And they identify the most significant SNPs. Then they do a projection. They're given their techniques that for 100,000 individuals, so if they go above from 21K to 100,000 and from 220 to 500, so we kind of try to extrapolate what will happen later. The runtime is 193 hours. When they talk about million individuals, they're starting to talk about years. And logistic regression, in comparison with this trend test, was prohibitively expensive, so they weren't able to get results. And they predict, both papers actually, make a prediction that if you use FHE or homomorphic encryption, it will be just impossible, even for the data set that they were using. So one prediction is a quote: it will take many years of computational or petabytes of communication, the scale of 1 million genomes, and are therefore not viable for large-scale GWAS. And the 2017 paper even gave an estimate of 10,000 slower than multi-party computation. So the good news for today is that doesn't seem to be the case in big time. So we, in this paper, we use actually homomorphic encryption, based on ring LWE. It's a modification of the Heen system. And we run 2 statistical tests, which one is essentially a chi-square test of a particular, which is equivalent to the one that I described in the Cho paper in the previous slide. And we also managed to get logistic regression approximation. We use the same data set, the AMD, And we run it on somewhat more individuals and SNPs, but the best part is that if you extrapolate in the same way that they extrapolate, it seems like that what we can get for chi-square tests is 5 hours versus 193 hours extrapolation in the previous study, and also for logistic regression, which was practically impossible to get something within hundreds of hours. The accuracy is similar in the chi-square because we could compare it. The logistic regression approximation obviously is higher since they couldn't get it, but it's good. When we compared it to unencrypted, it was quite good. Again, it seemed like there was no loss in accuracy. So here is sort of, we are comparing what we got with encryption for logistic regression. You sort of count sort of the highest places, SNPs that have association, and we see that for the top hits, we had no loss in accuracy. And even when you go to this polygenic scoring, so not just association, but prediction, it doesn't seem that we have a loss in accuracy. And this is some information about scalability, going from, going beyond, you know, the 100,000 individuals. And the way that we come up with the scalability results is that we sort of look at the time that it would take in terms of the number of SNPs and the number of individuals extrapolating from the experiments that have been done. So I think there's a lot of opportunities here. I kind of went into detail into this, even though this is really a practical and not a theoretical result, although there is a lot of theory here, because in order to get these results, one had to do clever data packing to pack things into the encryptions. One had to do approximation of the logistic regression, so had to do some data science and a lot of engineering optimization. But I think that there's a lot more to do, you know, to do this across institution to really, you know, go full force into this prediction world rather than just association. And if we kind of go away from GWAS, I think this is good news for homomorphic encryption, about the fact that it's really making giant steps going from theory to practice. There are lots of libraries out there now. The library that we use here is this Dualisade, and which is also in the context of, there's a public version of it, Palisade, which is what's being used in the paper, and there's a non-public version called Dualisade. And as you know, I think there's another workshop where standardization of these schemes is in progress. Okay, any questions? I don't know if we have time for questions. Probably not. I have time, another 15 minutes or something, right?
We have 15 minutes for questions.
Okay. Oh, well, then I'm going to continue, and I'll have a little bit less minutes for questions. So let's talk about robustness. So the second thing I want to talk about is about how to do accurate predictions when the test distribution adversarially deviates from the training distribution. And this is the paper with Adam and Yael Kalai and Omar Muntasar from TTI. And it's also a recent work, which is in submission right now. So again, adversarial machine learning, there's a lot been talked about in the last few years, especially in the context of self-driving cars and so forth, about how you can cause misclassification if you choose your test data in a clever way, sometimes even replacing your training, the training data by adversarial training examples. And the adversary, he may have black box access, still can be, he can fool you, and if he has white box access to your algorithm, even worse. So the current approaches are to define domain-specific attacks and prove that you could be robust against them. And in particular, it's been done in classification, in image classification. People looked at rotations and translations. I think there was a competition in NeurIPS where there were sort of 10 papers proposing different approaches to protect, and I think all but one was broken. But there might be news since then. I'm not really part of that community. It's sort of more of an adjacent member. So as cryptographers, it's natural for us to say, well, how do you know what you're adversary is going to do? How do you know what algorithm the adversary is going to be restricted to? We should consider worst case adversary. Maybe we can restrict them computationally by polynomial time, but we should not restrict the strategy. So that's really what this work is focusing on. We want to go beyond this idea of perturbation, and we want to get some kind of theoretical guarantees with arbitrary test examples. And what we get in a snapshot, if I don't have time to go through everything, is learning algorithms for any concept class of bounded VC dimension and for any adversarial test input distribution. So it sounds too strong to be true. And that's why I'm adding this qualifier when possible. So what do I mean by when possible? So if we think about pack classification, Valiant's definition, right? He's given a bunch of examples, x1 through xn in some distribution P and some labels. We can extend actually our work. It's not just 0 to Boolean labels, could be many classes, but let's look at Valiant. So these are either plus or minus, and you want to learn a hypothesis such that with high probability, usually use delta for that, the probability of a mistake is small. So the probability of a mistake is less than epsilon, or the probability of fit is greater than epsilon. And that is with respect to the same distribution of the examples, which makes sense. You've seen examples for distribution, and now you're going to be tested on the same distribution. Otherwise, it's like taking a class and then homework is about a completely different chapter. And anyone who has kids is like, that's not fair. Anyway, so the train distribution and the test distribution are the same. Now, so here's an example. You want to learn half spaces. Let's say plus is the positive. What you're trying to learn is this line, okay? And this is a possible candidate, that H is the right hypothesis. But let's say that now test come, and these are these spots. If they're in fact mixed in between the pluses and minuses, you'll do quite well. But what about if they're not mixed well? So in other words, let's say that they show up here, or oops, yeah, let's say they show up here. Then either one of these tests would do fine with respect to what you've seen, but not very well with respect to the test example. In fact, it's impossible. It's very easy to see it's impossible. Just choose one mistake and repeat it, you know, for your new distribution, where your test distribution is different than the train distribution. And this is not just a plus minus threshold, but you know, it implies to images. Let's say there's these papers, right, that talk about the fact that there's all these gender class, there's very big disparity when you do gender classification, when you look at, you know, white women versus women of color. And this is even when it's not adversarially, it's just a shift of a distribution. If you've seen a lot of gender, you know, white and men and women, and then you're seeing a different distribution in terms of the color, you might not be able to do well. And we are thinking of even a worse situation where this is an adversarially chosen. So it might be offensive videos or offensive pictures that have been selected in a distorted way so that you won't be able to identify, let's say, the gender. Another example is, let's say, the COVID-19, which is not such a politically charged example, where you might think of again, that, you know, we have a lot of information, a lot of training on flu, but when you come to find out something about COVID, these are the test cases. And these are very different, maybe the flu or maybe the population that you're looking at when you have the test is very different than what you've been trained on. So let's say you were trained in some city in China, and now your test is examples in the West. Is it going to look the same or not? So I just want to emphasize here that in terms of adversary, I'd like to even look at adversaries that not only that they have black box access, but maybe they even look at your classifier. So they know what you do. They have access to it, and now they try to trick you. And those are the kind of adversaries often in cryptography we look at, right? We have an adaptive adversary. You can look at the public key, you can look at chosen ciphertext. We would like to say that even in that case, that he shouldn't really succeed. So the question is, since it's impossible, how are you going to relax the model? So that's our also a very typical cryptographic question. Let's define it so we can get the best we can. And this happens all the time in cryptography. So there has been a lot of considerations of this in the literature, even going back to 57, and then some work by Rivest and Sloan in '88, where they say, you know what, why don't we let the learner abstain? So he can tell us whether it's a positive example, a negative example, or that he just doesn't know. So for example, on this black circle, he might say he doesn't know. They've shown actually that to get even there, to get sort of optimal in some sense that they define optimal, you need exponential number of examples. The thing is that this was really considered in all these papers for still the case of test equal to train. What we do here is we relax the model even further. So what we say is, yes, we're going to allow the learner to abstain, so he won't be able to tell us when he doesn't know, when he's never seen examples of this type. But in order to get good performance, what we're going to give the learner is, in addition to the examples that he's seen in the training time, he's also going to get these things in red, which are some example from the new distribution, which are unlabeled. So he's given some training example, telling him whether there's a plus or minus label. And in addition, he's going to get some, like you could think of it as a batch of what his test examples are going to be. And now using this, we're going to be essentially going to try to use the difference between P and Q to be able to tell when to abstain and when we have a shot to actually answer correctly. So is this reasonable? So in a minute, I'll tell you exactly what we achieved, but is it even reasonable to think that you're getting some examples from the test distribution? So sometimes yes, and this is called the transductive setting, where you get a whole bunch of test examples in batch. So sort of you know that that's what you're going to have to work well on. And even if not, if you have to do it one at a time in an online fashion, you can be adapted in retrospect. So you can think of it, things are coming, you might be making mistakes. After a while, you say, no, these ones, let me go back. These ones I can't really tell. So what can we get? We essentially can get, for everything for which there is, rounded BC dimension, we can use the empirical risk maximization, risk minimization results that are out there. And this is even though the training was from one distribution and the test from an arbitrary other distribution, the guarantee is the following. Low rejection, and so you could ask, what could you do? Maybe you could both not reject on the test and also not make errors. That's going to be impossible. So what we do is we show that you're going to get low rejections on P. So if it was a distribution which is the same as what you saw on the train, you're going to have low rejection and low error on Q. So it is possible that you will reject all of Q. But when you don't, when you actually do give it a label, it will be correct with high probability. So in particular, we define this, the rejection probability and the error probability, and we show that the sum of the two, that is, you're not going to reject much on the train distribution, you're not going to err much on the test distribution, and the sum of the two is square root of the VC dimension over n, where the number of your training examples. And we call this PQ learning, P for the train and Q for the test, and this, which is essentially a generalization. And this is a tight result. So can this be extended? What I've described so far was about supervised, where the training examples are supervised, and when it's realizable, meaning that there is, in the class that I'm looking at, there is actually a way to learn, there is a hypothesis which agrees with F. We have looked at extensions, as I said, to transductive, which means, I urge you to look at the paper, which means that it's not just that there's a distribution, but you actually give the adversary, you let the adversary first choose, and then you show him your hypothesis, and then he changes some examples. And then on that test set, you try to achieve what I claim we achieved. We looked at unsupervised, and we looked at agnostic. So to sum up, essentially, previously people knew how to do adversarial perturbations. It's a lot of work from recent years, or when there's like a particular, the distribution is a distortion of the training distribution, where we can really look at an arbitrary test distribution Q. Of course, our results are somewhat incomparable since these works don't reject, and we allow rejection. But I strongly feel that this is a very reasonable because it's impossible to do otherwise. Now, I know that I am not supposed to speak anymore, so I will just put one slide, and that is that I was going to talk about verifiability as a third thing that we inherit from cryptography. This is joint work with Rothblum, Guy Rothblum, Jonathan Schaefer, and Amir Yudayov. Again, this is online. And the idea here is we want to be able to ensure the machine learning models that are being claimed by a learner are accurate with respect to a given distribution, which is a very important goal. Our point of view is not an optimization point of view where we minimize the effect of bad inputs or systems where we have good platforms, but really we say we are not going to believe the machine learning person at all or the platform. We want to be able to prove to us that the model is in fact accurate with respect to a given distribution, this pink one here. And in order to do that, we define a new notion called pack verification, where we're saying that we want to say that the prover can convince the verifier to accept a particular hypothesis when the loss of the hypothesis, loss meaning the error that the hypothesis makes, is close to epsilon. So in other words, it's the sort of the best you can do. The optimal here might be if your hypothesis in the class, there is a hypothesis in the class that you're looking at which is perfect, the optimal would be 0. So in which case you want the loss to be smaller than epsilon. For all cheating prover strategies, you want to make sure that you don't accept something which is greater than epsilon. So if the error is larger than epsilon, you reject. If it's less than epsilon, you accept. Okay. And the most important, not important, the interesting thing here is that we want to do this in a way where the verifier works a lot less than the prover. So in particular, we're going to allow interaction, but the learner or the prover can have a lot more access to distribution and than the verifier. And also he might have a different type of access. So where he may do like membership queries to the distribution, so you can ask an X and get a label f of X. The verifier can only get pairs X f of X for, so where X is according to some distribution. And the question is whether having such limited access and maybe a lot less samples, can you convince the verifier that the hypothesis you're sending is in fact accurate, with respect to parameter epsilon? I just want to say that when the optimal is 0, it's kind of a trivial question. So the verifier just takes a whole bunch of random samples and he accepts it if he classifies all of them accurately, but it's interesting when you're talking about the agnostic case. So like if you're looking at a class where you actually don't have a perfect hypothesis, there's the optimal hypothesis. And now the prover is giving you a particular hypothesis H, and you want to see that he's done pretty well. So what he gave you is not too far from what he could have given you in that class. So what's difficult here is to estimate the optimal. It's not so hard to estimate how good the hypothesis that he gave you. You just test it on the random samples. The question was how good it is compared to the best he could have done. And that's where the challenge comes in. And that's where the prover needs to prove that this is pretty close to what he gave you. And there's a bunch of results, but the positive result that's interesting also for crypto is that we look at T-sparse Boolean functions. Those are the labels, Fs. And we use work by Kushlevitz Mansour and then Goldwasser-Levin, where they were talking about learning Boolean functions in Kushlevitz Mansour and then hardcore bit class security in Goldwasser-Levin. And we somehow use these algorithms, these learning algorithms, to show that we can actually pack verify such this class of functions, where the prover will have membership queries, but the verifier will only have random samples. And they will both run upon all time. And we use two-way interaction, so it's actually interactive. And this is quite interesting because if LPN is a hard problem, learning parity with errors, then there's a real separation here between prover and verifier. You cannot learn from random samples. You need membership query, and the verifier is able to verify from random samples. Now I'm done. Thank you.
Thank you very much. We have time for 2 questions. So if anyone wants to ask a question, please raise your hand on the participants list.
Nobody? Too fast, huh?
I have a question actually, but if somebody else wants to ask. Okay, I can ask you a question.
Sure.
So thanks a lot, Shafi. That was very nice. I want to ask you about the robustness work.
Yeah.
So you use the measurement of VC dimension, right?
Yeah.
So why is it like? Why did you choose this measure? Like, can we like measure in different ways using different tools there?
Yeah, possibly. We chose that because it seemed like a natural one. We wanted to have a reduction to say, what if you could do it when test and train are the same? Can you kind of use that as a black box and also be able to achieve the same, use the same algorithm in order to achieve, it's not the same algorithm, but use it as a black box or as a procedure in order to get a similar result or for the similar class when test and train are different. But I think that's a very reasonable question.
Okay. Thank you. There's a question, I think.
Okay. In the
Muhammad.
Yeah, he says also if VC dimension is not bounded, one cannot even do pack learning without attack. Oh, okay, it's more like a.
right. So I'm looking at, yeah. So he's answering your question.
Yeah, exactly.
But it could be, you know, something, you know, rather than using the empirical risk minimization, you could use something else. But this is sort of a natural thing to choose. I mean, lots of questions here. You know, we, in a sense, what the work does is it identifies a set where you're gonna, on which you should do well, or differently like a rejection set. And you know, there's a question about how do you define those sets? I mean, is there an implicit access to it or an explicit access to it? I think there's a lot of computational questions you can ask here because we looked at an adversary who's all powerful. So we just wanted to get a result for any Q. But having a computationally restricted adversary, I assume you could get stronger results.
Yeah, then we can. That's interesting. And so will we be able to have your slides for the people to see the papers you were referring?
Yes, sure.
Oh.
I may. Okay.
Okay, thank you so much.
Sorry, one last question, Sophie. So we have one more question. What kinds of ML models can we verify from Divya?
Ah, okay, good. So we did, we didn't look at, that's a good question to talk about. We looked at of a class of functions rather than models. So what you're asking is, could you verify everything that's like decided by a decision tree or, and so forth? Those are great questions. What we did is we looked at class of functions, like the Fourier sparse functions. We looked at threshold functions. Those we could verify. That's all we know at this point. But I would think that there's a lot of work to do here, not even just about classes, but also properties of the models, you know, like fairness or whatever other properties you might be interested in.
So many open questions in this field. Thanks a lot, Safi.
Welcome.
Thank
you for inviting me.
Bye-bye.
Bye.
And actually, Gilad